Hello everyone and welcome back to another math video. In this video we're going to start the discussion of antiderivatives. A function capital F is an antiderivative of the function lowercase f if f capital F prime of x is equal to f of x for all x in the domain of the lowercase f. So I'm going to give you an example. Let's say we have this function 2x. And we want an antiderivative. What we're trying to figure out is what can we take the derivative of to get 2x? Well, we could take the derivative of x squared, because if I know I take the derivative of x squared, I'm going to get that 2x. So we would say x squared is an antiderivative of 2x. But it turns out there's a lot of different antiderivatives for 2x. What if we were to look at x squared plus 3? If we were to take the derivative of that, we're still going to get 2x because the derivative of a constant is 0. So what if we were to take the derivative of something else, like x squared minus 17? Well, that derivative is also 2x. So we would say this is an antiderivative of 2x. So it turns out that there's a lot of different values we could use for that. And remember, this is going to be a transformation. So we could be really generic here and we could call all of those possible values C, where C represents some constant. So then we would say the antiderivative of 2x is x squared plus C. Remember that C, if you think back, the transformations would take that parent function x squared and it would shift it up or down depending on if C was positive or negative. So let's talk about some notation before we um, look at our integration rules. So we're going to talk about indefinite integration. So we're going to see a symbol that looks like this. It looks kind of like a stretched out S. That is the integration sign. The dx tells you what you're integrating with respect to. And then once we perform that integration, notice the integration sign's no longer there. Then this is the antiderivative. And then we're going to have that plus C on the end, which is called the constant of integration. This is kind of the opposite of taking the derivative. Now, really what we're doing is we're really thinking about that derivative and we're asking, how do we get back to the original function? If this is the derivative, how do we get back to that original function, x squared plus some constant? So let's look at some integration rules. So if I want to integrate, here's my power rule. I'm integrating x to the n with respect to x. So this sign tells me I'm integrating. This tells me I'm integrating with x's as my variable. So my rule is I'm going to add 1 to the exponent, and then I am going to divide by the new exponent. And then we're going to have plus c. So for instance, suppose we want to integrate x squared with respect to x. We're going to add 1 to the exponent, and we're going to divide by the new exponent, and then we're going to have that plus c on the end. And you can always check it by taking the derivative. If I were to take the derivative of this, I would keep the 1/3, because remember this is multiplied by 1/3. I would bring that exponent down and I would subtract 1 from the exponent. And we know the derivative of a constant is 0. So that's going to give you that x squared, which is what we started with there. That was your lowercase f of x from that. definition we talked about a minute ago. Let's look at another rule. Let's say we want to integrate a constant. So that's going to be k times x plus c. So for example, if I want to integrate the constant 3 with respect to x, it's going to be 3x plus c. Again, we could check it. If I take the derivative of this, I'm going to get just that 3. I want to go back to the power rule a minute. This works as long as n is not equal to -1. If n is equal to -1, it's going to have a special derivative, which we'll talk about here in a little bit. Let's talk about sum and difference. So if I integrate a function f plus a function g with respect to x, that's the same thing as integrating f and g separately. And then adding them together. And the same thing would be true if I'm subtracting, so I can combine those rules that way. For instance, suppose we wanted to integrate x cubed plus 3 with respect to x. So I could think about integrating x cubed and then integrating 3. When I integrate x cubed, I'm adding 1 to the exponent, dividing by the new exponent. And then when I integrate 3, I'm going to get 3x, and then we're going to have a c on the end. Okay, so no, we only have to have one c. If we integrate this, we could have a plus c here and plus another c here, but a constant plus a constant is another constant, and we only have to write that constant once. So that's why that just one plus c would be sufficient there. Let's talk about some trig rules. If I want to integrate sine, I'm going to get negative cosine. If I integrate cosine, I'm going to get sine. Okay, the reason that works, we could take the derivative. Derivative of sine is the cosine. The derivative of negative cosine is the positive sine. If I want to integrate secant squared, I'm going to get tangent of x. If I want to integrate secant tangent, the derivative of the secant is the secant tangent. So when I integrate that secant tangent, then I'm going to get secant. We could talk about the antiderivative for cosecant squared, which is negative cotan of x, and the antiderivative of cosecant x cotan x is negative cosecant of x. Now let's talk about our log and exponential rules. If I integrate e to the x with respect to x, it's going to be e to the x plus c. The derivative of this is that. If I integrate 1 over x, we had a function that we took the derivative of to get 1 over x, and that was your ln function. Okay, but notice this is going to be the ln of the absolute value of x plus c. The absolute value is going to be important because remember, with the ln function, we have domain restrictions. And then let's look at a few of the inverse trig functions. If I want to integrate 1 over the square root of 1 minus x squared. That was your arcsine function. The derivative of arcsine is that. If I integrate 1 over 1 plus x squared, this is arctan. And then if we integrate 1 over absolute value of x, square root x squared, oops, excuse me, that's not absolute value. X square root x squared minus 1. That's going to be inverse secant. And then I'm going to talk about one more. What if I have a constant times a function and I need to find the antiderivative? There's a rule that says that I could pull that constant out and then integrate the function. So we're going to take all these pieces and we're going to put them together and we're going to integrate. So let's look at a few examples. With this first one, we can think about integrating each piece separately. So let's go back to this rule and let's do an example. What if I have 2x to the 5th and we want to integrate? This rule says I could pull the 2 out and then integrate x to the 5th. And then a rule for that says I'm going to add 1 to the exponent, divide by the new exponent. Don't forget the plus c. So we're going to have 2 divided by 6, which is 1/3. So you can see how that rule is working. We can think about pulling that just 2 to the side, that number that's in front, and then adding 1 to the exponent, dividing by the new exponent. We're going to use that same information here. So it's going to be a combination of that rule with that sum and difference rule up here. So let's look at that. If I want to integrate 5x cubed, I'm thinking about bringing that 5 to the side. I'm going to add 1 to the exponent of x and divide by the new exponent. Same thing here. Pull that -7 off to the side. I'm going to add 1 to the exponent, divide by the new exponent. Pull that 3 over. Add 1 to the exponent, divide by the new exponent. And then when I integrate a constant, it's going to be the constant times x, and then plus c. So there's my antiderivative for that function. For b, we're going to have to think about some of those techniques that we talked about when we were differentiating. So we don't have a quotient rule or a product rule, really, when it comes to integration. So we have to simplify things. So I'm going to split that numerator. This is 4x to the 1/3 divided by x. So when I divide and I have the same base, I'm going to subtract the exponents. Same thing here, 1/3 minus 1 is going to give me a -2/3 for that exponent. So now I'm going to add 1 to the exponent, divided by the new exponent, 4. And I'm going to add 1 to the exponent, so -2/3 plus 1, which is 3/3, would give me a positive 1/3. And then I'm going to divide by the new exponent. And then we need to clean this up. So this is x squared over 2. When I divide fractions, I keep change flips, so I can think about multiplying by that reciprocal, which would be 3. So I'm going to get 1/2 x squared plus 12x to the 1/3 plus c. Let's look at this one. So we could think about pulling that 4 out. And this fits my inverse tangent function. So this would be 4 times arctan of x plus c. And then let's look at that next one. When I integrate tangent times cosine. So we're going to think about the rules that we have, and we don't have something that we take the derivative of to get tangent cosine. So let's see if we can rewrite everything in terms of sines and cosines. Tangent is sine over cosine. And this is times cosine. And those cancel. So this is really asking us to just integrate sine of x. And when I integrate sine, going back to our rules up here, we're going to get negative cosine. So this would be negative cosine of x plus c. Now, if we have enough information, then we can solve what's called an initial value problem. And all that means is that you have enough information to be able to find c. To find c, you have to have a point on the graph. So let's look at an example. We want to solve the initial value problem, dy over dx equals sine of x, and they're telling us that y of 0 is equal to 5. So this is a point that's on the graph. This is saying when x equals 0, y is equal to 5, or we're looking at the point 0, 5. So when we solve this, and this is called a differential equation, then you want to think about getting grouping variables. So you want all y stuff on one side and all x stuff on the other side. So we're going to multiply both sides by dx. So now I've got dy on the left, and this is sine of x times dx on the right. And now we have done what's called separating variables, and we can integrate. And remember, there's an understood 1 in front of that dy. So when I integrate a constant, I'm going to get 1 times x here. And then over here, when I integrate sine, I'm going to get negative cosine of x. And then we're going to have a plus c. So when we think about integrating, sometimes we think about adding plus c to both sides, but that's not really necessary, because if I have a constant here and a constant here, then when I combine them, I can combine them on one side and I'm still going to end up with a constant. So it's not necessary to write it on both sides. We're just going to put the plus c over here. Oops, this guy should be a y. So we have y equals negative cosine x plus c. So now let's substitute in our point. We have the point 0, 5. My y value is 5. X is 0. So we have 5 equals negative cosine of 0, which is going to be a negative of 1 plus c. So 6 is equal to c. So my solution is going to be negative cosine of x plus 6. So I want to take a minute and graph this in Desmo so you can see what's going on. So I typed in my antiderivative, negative cosine of x plus c. Here's my slider, and you can see that c is going to shift this thing up and down. We wanted to go through the point 0, 5. So there's that point we want to go through. So we're shifting until we get to where we can go through that point. And we said that y was going to be equal to negative cosine of x plus 6. And that's the particular solution that goes through that point 0, 5. So let's solve another one. And this is where you may want to pause the video, try it, and then come back and check your answer. So we're going to start in the same way. This means that when x is 1, y is 2. And we're going to separate the variables. So I'm going to multiply both sides by dx. So I'm going to have dy equals 3x to the negative 2 times dx. And then we're going to integrate both sides. When I integrate dy, I'm going to get y. When I integrate here, I'm going to add 1 to the exponent. Negative 2 plus 1 is a negative 1, divided by negative 1. And then I need a plus c, and I'm going to put that plus c on the right-hand side. So I'm going to have y equals negative 3 over x plus c. And then we're going to substitute in our point, 1, 2. So y is 2 when x is 1. So 2 equals negative 3 plus c. So 5 is going to be our c value. So then our solution, this is called the particular solution, is going to be negative 3 over x plus 5. So that would be the solution to this differential equation.